So starting true or false, and I'll use polls for these like you usually do. So first we have aldehydes and ketones undergo nucleophilic acyl substitution reactions because hydrogen and alkyl groups are good leaving groups. So think about what kind of reactions typically did with aldehydes and ketones. Maybe think about how good of a leaving group hydrogen and alkyl is, like methyl, ethyl, propyl, just carbons. Like think about how those are in terms of leaving. Sorry, the key points. I'll give it like 15 or so more seconds. And then I know it's late in the semester, but I just want to kind of say I think it's good to put something, even though like I'm not grading you on participation, because if like you put something and you're wrong and I know like a bunch of people got it wrong, then I can explain it better. But if I don't know how people are doing, I might just assume you guys understand. So, you know, it's always good to participate so we can see how you guys are doing. But anyway, it was much more than 15 seconds. So one of you said true, 4 said false. This one, well, we can kind of run it down for people who might not know. An aldehyde or a ketone would be something with a carbonyl and a hydrogen or another alkyl group attached to it. And remember, like when we were doing reactions with these, the mechanism would be like a nucleophile would attack the carbonyl carbon. And then you'd get an alkoxide. Then you'd have your nucleophile attached. And if we were doing a nucleophilic acyl substitution, we'd be like kicking out a leaving group and forming the carbonyl in the second step of the mechanism. But what we have here is either a hydrogen or an alkyl group. It depends on if it's an aldehyde or a ketone. But either way, that's what we would have as a potential leaving group. And those are both very bad leaving groups, because if you kicked out a hydrogen, you would get H-, which is hydride. That's super reactive, and things that are very reactive aren't good leaving groups. And like if R was a methyl group, then just as an example, you'd form SCH3-, which again is very, very reactive. So it's a terrible leaving group. So you can't kick those out because they're very bad leaving groups. And you should recall, like, because we've done these reactions and mechanisms, instead of kicking the leaving group out, we would usually just protonate the alkoxide. We wouldn't reform a carbonyl. And then you'd form an alcohol. So we were doing nucleophilic acyl additions with aldehydes and ketones. That's what this is an example of. Not substitution, because we can't do substitution since we have bad leaving groups. So this was false, which the majority of you who answered got, but just in case people were confused, that's the rundown. Next one, reacting diazomethane with a carboxylic acid yields a primary amide. And this like probably got covered quickly last week, but it was on the slides. It's something Okuda will want you to know about. So if you don't know it right now, that's okay, but we'll eventually. I'll give it like 10 more seconds to try to give everybody a chance. Okay. So it's time 4 set true, 3 set false. I actually have an example of one of these reactions later, so I'm not going to say like what exactly it does make, but I will just say this is false. Doesn't make a primary amide. It makes something that's kind of primary in a sense, but it's not an amide, so that's why this is false. And again, like I'll explain what it does make later, and if you know it, then that's good. But yeah. Okay, next one. Carboxylic acids and derivatives prefer acid-base reactions over organic ones with the carbonyl. So just to kind of show you what I mean, like if you add a nucleophile, you know, it's usually going to attack here at the carbonyl carbon. And then if you were to add a base to this, then it would take the proton there. So it's basically just saying like, if you had a nucleophile and a base, like which one's going to have a preferred reaction, what will happen faster is what this is saying. Just something that has come up a couple times. Okay, like 10 or so more seconds. That's most people. So here, 7 true, 1 false, and the majority is good here. This one true. Just like what I've been saying a couple times in the past, and what Okuda has probably said, is like acid-base reactions are always stirred organic ones. And organic is like nucleophile and electrophile reactions we look at a lot. So that's the point this was getting at. Now, hydrolysis of any carboxylic acid derivative besides ester yields carboxylic acid. And remember, hydrolysis is adding water. So this is saying if you add water to anything in this chapter besides ester and carboxylic acid, like 5, 10-ish more. Okay. So 5 said true, 3 false. The majority of this statement is true. Like hydrolysis of carboxylic acid derivatives does yield carboxylic acids. It's a true statement, but this part excluding thioesters is what makes it wrong. Thioesters are still a carboxylic acid derivative. You didn't talk about them much, and you don't have to know a lot about them, but this is one thing you do have to know. They're still carboxylic acid derivatives. They still do hydrolysis like anything else would. So that's why this is false. Because thioesters would also give you carboxylic acid if you hydrolyzed them. And that's actually the only reaction you have to know for thioesters. You just have to know that you can add water to them to make a carboxylic acid. You don't have to know how to make an ester or an amide or anything else out of them. Okay, next one, hydrolysis of an ester in basic conditions is called saponification. This, I think he kind of skipped over it in lecture last week, but it's on the slides, so I think it's still fair game. And maybe he talked about it in class today, but like this is a term that you will have to know most likely. Right, I'll end it here. So 7 said true, 1 false. This is kind of just a definition. I don't have much of an explanation for this. It's just true. That is what saponification is. And there's an example of it, like right here, because we're adding water to an ester and we have basic conditions. That's saponification, just as an example. Next one, alcoholysis reactions can occur under acidic or basic conditions. Just think about what contexts you've seen those reactions in. And remember, hydrolysis is adding water to a carboxylic acid derivative. So if you think about it, if you're not familiar with this term, that just means you're adding an alcohol to a carboxylic acid derivative. It's like reacting an acid halide with an alcohol or a carboxylic acid with an alcohol or anything else. If that context helps at all. Give it like 5 or so more seconds. So here, 3 said true, 5 false. This one is true. I'll just say, like, as an example, if you're going from ester to ester, which isn't something he talked about, but that can happen under either acidic or basic conditions. But like, even without that, like you've seen, if you have an acid chloride and you add an alcohol to it, remember we also wanted to have pyridine present. And that was a base, so we were adding an alcohol under basic conditions here. And then if you were to start with carboxylic acid and add an alcohol to do alcoholysis, we would have acidic conditions, we'd have an acid catalyst. So just 2 separate examples to show you it can happen either way. It doesn't have to be one or the other. So that is why it's true. And last one, acid chlorides can react with ammonia, primary, secondary, or tertiary amines to form an amide. Okay, that was relatively fast. So 2 said true, 6 false. And this one is mostly true, kind of like D up here was mostly true, but it seems like you guys caught on to this. That's the only issue with this. you can't make an amide out of a tertiary amine. So that's why this is false. But everything else about that was true. You can make amides out of any other kind of amine. So that's question 1. Took a while, but that's that. I'm going to go ahead and move on. If there are any questions, I can bring this stuff back up and go over them. But if you don't stop me, I'll just keep going. So here's that saponification reaction. And again, like he didn't talk about it in class. I'm not sure why he skipped over it. He hasn't in the past, but I'm assuming it's still fair game because it's in the slides and it's in the book. It might be good to ask him to confirm, but until you know for sure, I think this would be something that's good to be aware of. So that's why we're going to practice it. And it's not going to be too different from what you've seen before. So hopefully that helps make it a little less stressful. So we're adding water and hydroxide to an ester. What would make sense as a first step of this mechanism?
Protonating?
We would do that if we had an acid catalyst around, right?
The OH attacks the carbonyl carbon.
Yeah, so I know a lot of the time we do protonate this. It just depends on the conditions, basically. So even if you don't remember a mechanism off the top of your head, that's a good thing to look for. If you see acid here, like H3O plus or HCl, then you would protonate that first. But otherwise, yeah, the first step would be whatever your nucleophile is. Here it's hydroxide. It will attack the carbonyl carbon. And then push the pi bond up towards the carbonyl oxygen. So this would be like an example of a base catalyzed mechanism. Because we're adding a strong nucleophile, there's no acid, so we just go straight to the nucleophilic attack. And what should we do now that we have this intermediate with the alkoxide?
Should reform the the double bond.
And then what will happen?
Yeah, the O and methyl will leave. Sorry, I don't remember what it's called. The ester.
Yeah, just the ester part of the oxygen. And when you do that, you form a carboxylic acid. And a lot of the time you would say like this is the end of your mechanism because like we're adding water. We want to form a carboxylic acid and we did. So it looks like you're done. But with this mechanism, there is a bit extra. And I know that he wants you to show this if he asks you about this on a test. This leaving group we just kicked out, it's an alkoxide. It's an oxygen with a negative charge. And what could this behave as in a reaction? Like acid, base, nucleophile, electrophile. Nucleophile, yeah, because it has a negative charge. And what else?
A base.
Lots of the time, nucleophiles are also bases. So it could act as a nucleophile, but if it did that, like it would be attacking here. at the carbonyl, and then you can see like we're just going back to this, we're going backwards. So that is a thing that can happen, but it doesn't get us anywhere for this mechanism. But in terms of a base, like it's a pretty good base. We have a carboxylic acid. Acid is in the name of the functional group. So these can do an acid-base reaction. You can take the proton. And you do have to show this because this is something that would happen. You can't really stop it. So even though we already formed the product, it's not going to stop there in the mechanism. This is always going to happen. And then you form a carboxylate, and we formed an alcohol as our byproduct. So now we have a negative charge on the oxygen here. You never want to end with a negative charge on something. You usually want it to be neutral. So we would just want to protonate this for the last step. And we can protonate it with water. It's not a super strong acid, but it's good enough to react with this base. And then you get your carboxylic acid again, but this time it's satisfied. It's not going to react anymore. You form OH minus, which was our base catalyst at the beginning, so we reformed the catalyst we started with, which is the definition of a catalyst. So most of this like isn't anything new, like up to this step that I'm circling. Like you have the nucleophilic attack and then you reform the carbonyl and kick out a leaving group. Like that's the same stuff we've seen in the past. So that's not new. The only real difference here is just like when we formed this leaving group, it reacted with our product, and you have to show that. He wants you to show that. So don't forget about these last two extra steps. So are there any questions about this before I move on? All right, if there are, feel free to tell me to go back. Here we have an amide and we're adding water, hydroxide, and heat to it. So the conditions are fairly similar to the last one, just heat, and we're starting with an amide instead of an ester. What should the first step of the mechanism be?
OH attacking carbonyl-carbon.
There's no acid, so it will be another base catalyzed. And it looks basically exactly the same as the last one. And now what should happen? It's going to follow the same general pattern that most of these acyl substitutions do.
Reform the double bond again.
And kick out the leaving group. And this is actually fairly similar to the last one for saponification, because what you kick out is the leaving group, NH2 minus. This is another base, like it has a negative charge and it's fairly reactive as a base. And the carboxylic acid is still an acid. So it's actually going to do the same kind of thing. This doesn't always happen, like it depends on the leaving groups. So like with esters and amides, this does happen. These are fairly reactive leaving groups. With the other ones, it doesn't happen. So yeah, this is why it's important to make a bit of a distinction. So just like before, form a carboxylate, and you get this as a byproduct. And then you just want to protonate this carboxylate with water, like we did before. And then you end up forming hydroxide, which was our catalyst. So that's good. It got reformed. So I erased it, but hopefully you can see like this is fairly similar to the saponification mechanism. The only difference was we started with an amide, but it's basically the same step in the same order.
Does this one have its own name?
Not that I know of. It's just hydrolysis of an amide. Good question though, because I know the last one did. That just had a name because that's a way that people make soap. So it has a special name because of the soap. That actually might be something he asks too, but I don't know since he didn't really talk about it. I just want you to know the name. But anyway, last mechanism, we have an amide and we're adding water, acid, and heat. So what should the first step of this mechanism be?
Would this one be protonating?
Because we have this acid here. It's going to take a proton from H3O plus. Positive charge on the carbonyl oxygen. What do we typically do when we have this positive charge on the oxygen?
In this case, it wants another bond, right?
Yeah, we like
Resonance, right?
basically, yeah, which is basically like giving it another bond. So yeah, that's one way to rationalize it.
Would water come in and attach itself to the carbon?
You can show that at this step, but I think Okuda wants you to show the resonance form first, even though the book doesn't. Just because like when you show the resonance form, you have a carbocation that's a very strong electrophile, so it makes sense for water to come. And if you were saying that about this step, then my bad, I misunderstood. But yeah, like I don't think he wants you to show like this kind of thing, combining these two steps. You could theoretically, but I don't think he likes that. Okay. So at this point, like there's a positive charge on the water here. And we still have our leaving group and our carbonyl oxygen still has a hydrogen. So here, like I honestly don't think he'd ask you this mechanism just because it would take a lot of steps without combining steps. But I'm gonna combine some steps, so I'll say like do a proton transfer here between the nitrogen and the water we just added. And that forms NH3 plus. As a positive charge, it's a better leaving group now. And then you can kick out the ammonia. Form the carbonyl. And then last, you'd want to deprotonate the oxygen with a positive charge. And you can do that with.
Could you not deprotonate with the NH3?
You could, and I think that's perfectly fine too, actually. I'm mainly showing it with water just because when you do that, you form H3O plus when you protonate it. And just like how we reforms the hydroxide at the end in the last two, like we're reforming this, and that was the catalyst we used, so it makes sense for it to like come back at the end. But this is also a good base, so it could also do that. So yeah, that detail is probably not important, just whichever one decide on. Okay, so yeah, I'm, like I said, I'm honestly not sure if he cares about like the order or anything of like all these proton transfers and when you kick out the amine, but it like in some order you have to do like take this hydrogen away, kick this nitrogen out, like reform the carbonyl, and then take this hydrogen away. So there's like a lot of things to do. I think he'd be understanding if you combined steps a bit, like how I did here. Okay. We'll go ahead and move on as usual. Tell me to go back to for a question. This is something you kind of briefly talked about in class. I just want to kind of go over a bit here. So like you can explain the reactivity trends a little bit between the different functional groups in chapter 21, like explaining why an acid halide is more reactive than an amide. And here is an acid chloride. Here is an amide. And I give a hint saying, consider how strong of an electrophile the carbonyl carbon is. That's important because remember, we're doing nucleophilic acyl substitutions. That's the reactions we're doing with these. And in these reactions, like you have some sort of carboxylic acid derivative and a nucleophile is attacking the carbonyl carbon. That's always going to be a main part of the reaction. So anything that makes the carbonyl carbon a stronger electrophile will make this more reactive, because then it's able to react more easily with the nucleophile. And anything that makes the carbonyl carbon a weaker electrophile would make it less reactive for the same reasons. So for both of these, like they have this dipole with the oxygen. And when we look at an acid chloride, like what can we say about the chlorine? Like what is it doing in terms of like maybe inductive effects? Like would it be donating or withdrawing electrons from the carbon?
Withdrawing.
Yeah, because if you remember, like it's a halogen, it's on the far right of the periodic table, so it's very electronegative and it pulls electrons towards it a lot. So that's something you can consider for an acid halide. I will say for an amide, like you also have that dipole. It's not as strong because nitrogen is less electronegative than chlorine. So that would make that induction a little weaker. That's one detail. And there was another thing that you saw in class. I think Okuda went over it with amides. I'll give a bit of a hint. There's a lone pair on the nitrogen. And we have a double bond right here next to the lone pair. So for amides, you can draw a resonance form. Puts a negative charge on the oxygen and a positive charge on the nitrogen. And in both resonance forms, there's like a double bond on the carbonyl carbon. So like you can kind of say the nitrogen is donating. Oh yeah, that's also part of it. The resonance forms, like the more resonance it has, the more stable it is, so less reactive. That is a good point. More stable, so less. And just thinking about like the electron donating or withdrawing effects, like it's donating electrons by resonance. And chlorine, like it does have lone pairs, but it's not as willing to do that resonance form as nitrogen because it's more electronegative. So if you were thinking, why doesn't chlorine do that too? It's basically just because it's more electronegative. I don't think you'll ever see an example of a chlorine with a positive charge. And that's what you would get if you drew that resonance form like we did with the nitrogen. So that's just something to think about. Like it's something you wouldn't normally see. So it wouldn't make a lot of sense to show. So the nitrogen, you can think of it as donating electrons. And by donating electrons, it makes the carbonyl carbon less electrophilic. So that makes it a less reactive thing. And then the chlorine withdraws electrons, that makes it more electrophilic. So more reactive. So just think about these general concepts that are like from 112A, like induction and resonance. They help you explain the reactivity trends we've been looking at. Okay, are there any other questions about this one before I move on? Okay. Here we have a carboxylic acid and we're adding CH2N2. This is a pretty unique reaction. Does anybody remember what the product should be? Or maybe what this reagent is called? If you don't remember the product.
Is this the reaction where you replace the OH with the reagent?
It's like, it's in that same vein because it's still from chapter 21. This is fairly unique. Like, it's not going to follow the same mechanism, and you don't have to know the mechanism, you just have to know the product. Which is a bit unexpected. So I should erase that. This is diazomethane. It's something I referred to in the true false earlier. So that's its formula, CH2N2. And it will give you a methyl ester, which you wouldn't normally think looking at this reaction in the context of other ones. So might just be good to memorize. So this is what it will lead to. And it's always going to be like this. It doesn't matter what carboxylic acid you have. If you add diazomethane to it, you'll get a methyl ester. And on top of the methyl ester, you also get an important byproduct, which will hopefully make sense and be a little easy to remember. There's nitrogen here in the reagent, but it's not anywhere in the product. So
Yes.
yeah, you form N2 gas. And that leaves, so that drives the reaction forward. That's why this exists. Like, you can make methyl esters in other ways, but this is a good way to do it because that makes the reaction pretty fast and easy.
Could you add more carbons with this, or is it just the methyl?
It would just be the methyl, I think.
Okay, thank you.
I'm kind of thinking, like, theoretically, you could probably have the N2 somewhere else, like in a different kind of carbon, but I don't know how well the reaction would work. So at least for this class, yeah, it's always going to add a methyl group. Okay. Next we have an ester, and we're adding one equivalent of methyl Grignard and an acid. What kind of product should we make here? And I did specify, I normally don't, but I specified one equivalent. So yeah, normally we would make an alcohol, because if you don't specify any amounts, then you assume you're adding excess of a reagent, you're adding enough to completely react. But if we're adding one equivalent, then, like, let's go through this briefly. This is the mechanism the Grignard would do. It would attack the carbonyl carbon, get an alkoxide. You added a methyl group, and then you would reform the carbonyl and kick out your leaving group. And the acid's going to protonate the alkoxide. I'm going to kind of ignore that. But like when you reform the carbonyl, you get a ketone. And since I specified one equivalent, we're not going to add a second one to this. Normally we would add a second equivalent because we're adding excess. So it would react with the ketone, and that's what would give you an alcohol. But yeah, I'm kind of repeating myself a lot. Because there's one equivalent, it's not going to keep going. It will stop at the ketone. So this is just another thing to keep an eye out for. The conditions are important. If it's not specified how much you're adding, assume there's excess, and then you would get an alcohol. So, and that's always been the case. It's not just with Grignard reactions. If it's not specified, assume you're adding excess. But as you might have seen today, or you'll see on Thursday probably, we're going to start seeing a lot more reactions where like the number of equivalents we're adding like this is really important to pay attention to, because like one equivalent versus excess versus two or whatever, like it makes a big difference on what reaction happens. So it is good to pay attention to. Okay, so kind of tangent, but hopefully like if you haven't seen that yet, this is showing you that it's important to look for those details. Here we have a carboxylic acid and we're adding an ethyl thiol with catalytic anhydrous HCl. Before thinking like necessarily about what the product is going to be, these are pretty specific conditions that we've only seen for like 2 reactions in the past. Does anybody remember what reactions these conditions were used for?
One was the involve acetals.
Yeah, it was for Fischer esterification and acetals. So like we're not adding an alcohol, so we're not doing one of these, but the conditions are exactly the same. So maybe it will be similar. That's just something to pay attention to that might help. And we're not going to be doing acetal here, even though like the conditions could fit it, just because like we're starting with a carboxylic acid and acetal reactions are for aldehydes and ketones. But we might be doing something similar to a Fischer esterification because we have a carboxylic acid and we're adding a thiol, so it's not an alcohol, but it's just the sulfur analog of an alcohol. A lot of the time they can react pretty similarly to an alcohol, and this is one of those cases. So like if we were to add an alcohol with these conditions, we would get an ester. We're adding a thiol with these same kinds of conditions. So instead of an ester, we should get a thiol ester. It's the same kind of reaction. And I don't know if he would ask you to show the mechanism, but if he did, it would be the Fischer esterification, but with a sulfur instead of an oxygen. So don't be thrown off if he ends up throwing that at you. And this is the only other thing you need to know about thiol esters. You have to know like that you can do hydrolysis with them, and you have to know how to make them, but they're made the exact same way esters are. So just remember that they're made the same way esters are made. Next one, we have an anhydride, and we're converting it into an amide. What do we need to add to it for this transformation to work?
2 equivalents of methylamine.
Yeah, actually, I know you have to add 2 equivalents for an acid halide, so something like this. If the book said you need 2 equivalents, then I might have forgotten, but at the very least, yeah, like what we do have to add for sure is a methylamine. And it probably wouldn't hurt to put the 2 equivalents. I just honestly don't remember if that's a detail that we need. But yeah, at a minimum, this, because you add amines to make amides. Okay. So you might want to check the book to make sure whether or not that's the case, adding 2 equivalents for acid anhydrides. It's just as a little homework. Next one, we have an acid chloride, and we're adding Grignard reagent to it and an acid. So what kind of product should we make here?
Tertiary alcohol.
Yeah, that is what we want to happen. But like this doesn't come up very often, but there's a semi-acidic hydrogen on a nitrogen. It's not a very acidic one, but it is acidic enough. And Grignard reagents are very strong bases. So this isn't something I've put on a worksheet before, but this is another functional group that doesn't work with Grignard reagents. It's going to do an acid-base reaction. The Grignard will take that proton and just kind of consume it. So yeah, normally we would make a tertiary alcohol here. We would have added free propyl groups there. It's just because of the amine. So nothing ends up happening to the acid chloride. And we just formed propane as a byproduct because we protonated that. It's just like, remember, Grignard work with OH, NHR, or COH. And there are probably other functional groups that it doesn't work with, but these are the main ones that are likely to pop up on a test. Now we have an amide, and we're adding water and hydroxide. What kind of product should we make from this? If any product. So, oh, go ahead.
I was gonna say this would just put in alcohol or make a carboxylic acid, right? And then
Yeah.
kick out the NH2 or NH.
that is like what the conditions are for. It looks like a hydrolysis reaction. The only caveat with this, and I don't think it was emphasized much, if at all, in lecture, but I'm pretty sure it's still important. I didn't really emphasize it, but like this is the same kind of reaction. We have an amide, we're doing hydrolysis with hydroxide. But then I also had this heat here when we did the reaction before, and you need that for amides because they're very unreactive. We kind of discussed they have the resonance that makes them unreactive, so they react slow. Without the heat, they basically don't react at all. So normally, yeah, this would give us a carboxylic acid, but it's because of the lack of heat, it doesn't work. So that's another detail that's important. Without it, it doesn't work. So yeah, a little tricky, but hopefully that prepares you in case Okuda does it. Here we have another amide, and we're adding LiAlH4 and an acid. What kind of product should we make out of this?
Is this NR because it's tertiary?
I think it works with tertiary ones too. I could be mistaken, but I think I've seen examples.
Oh, so then you replace the double bond to the oxygen with 2 hydrogens?
Yeah, you just reduce this basically. And then the nitrogen just sticks around. So when you add those hydrogens to get rid of the oxygen, you end up making an amine. So like normally, if you added this reagent to a carboxylic acid derivative, you would get an alcohol. Like that's the case with all of the other ones, but with an amide, you reduce them to amines. So it's a little different. It's important to remember that difference. And I don't think you'd have to know the mechanism for this one just because like we're completely kicking out this oxygen. So it must be a little different from the others. But you should know that it makes amines. Okay. And the last one here, we have an alkene and a thioester, and we're converting it into a carboxylic acid. What conditions could we use for this transformation? What do we typically add to carboxylic acid derivatives?
H3O plus?
Yeah. Water, basically. So water and acid, H3O plus, or hydroxide, NaOH. But like acidic or basic conditions, you just have to add water, basically. Because this is just hydrolysis, just like it was with amides and esters that we did earlier, and we've done it with other groups too. It's just an example of hydrolysis. So a reaction like this, like I said earlier, this is the only reaction that you will have to know for thioesters. So if you want to make a note of that, feel free to. It's the only reaction you have to know about that you do with thiol esters. Okay.
This is when the H2O would attach to the carbonyl-carbon, right?
Yeah, it depends on the conditions. Like for the exact mechanism, like if I had the H3O plus, then we would protonate this first and then do the
Okay, right.
resonance, and then the water would attack.
Oh, and that's the other way if it's NaOH. Right?
Yeah, if it was the hydroxide, then it would just attack here immediately. It's like the acid versus the base catalyzed. It just depends on the conditions.
Okay, thank you.
That's a good question. Like, it's the same product either way, just the mechanism differs, and you do have to know the difference. Good to think through. Okay. If there were any other questions, can go back. Otherwise, I'll kind of just keep going. So now we have some synthesis, and I will say this first one, I don't think something like it would come up on the exam. I think it's a little hard to wrap your head around on an exam. I'm not saying it couldn't, but it's just a little less likely. But we're starting with, in terms of functional groups, we're starting with an aldehyde and an amide. So it's just good to take note of that. Recognize what you're starting with and what reactions you could do with these functional groups you're starting with. And then another thing to notice is like we started with a linear structure and we end with a cyclic structure because it's like a ring at the end. And if you ever go from linear to cyclic in a synthesis, then you had to do an intramolecular reaction. So that's just a little thing to take note of if you have something like this on a test. If you start linear, you end up with cyclic, you have to do some kind of intramolecular reaction. And which exact one you did, you can usually figure out if you look at what functional group you're ending with. So this is our functional group. It looks pretty weird because it's cyclic, but does anybody recognize what functional group this is? We have a carbon double bonded to a nitrogen.
I want to say nitro, but I don't think that's right.
A nitro would be
Triple, right?
like NO2. Oh, if you said nitrile, yeah, that's a carbon nitrogen triple bond. I might have misheard you. Yeah, not quite a nitrile. So it looks pretty funky, but this is just an imine. Remember, like if you have an aldehyde or a ketone and you added like NH3 as an example, like certain kinds of amines, if you add them to aldehydes or ketones, you end up with this. Yeah, you end up with this kind of functional group. You end up with a carbon nitrogen double bond. So it's been a while since we've looked at like these aldehyde and ketone reactions, but the final will be cumulative, so it's good to review. That's what this functional group is. Just looks weird because it's cyclic. But once you recognize that, like that tells you, okay, like you had an aldehyde or ketone react with an amine. Like that is the only way you could have made that functional group. And once you recognize that, that kind of helps you figure out like maybe how to start. Like we already have an aldehyde right here. So we have one component of what we need to make the imine. But this is an amide, it's not an amine. And even though they sound and look fairly similar, they react very differently. So we basically have to figure out how to turn the amide into an amine. That's the main part of the synthesis to piece together. And we actually just saw an example of this a few minutes ago. What can we do to convert the amide to an amine? What kind of reaction could we use?
LiAlH4.
But there's one problem with that.
It would also, wouldn't it reduce the other carbonyl?
Yep, it would also reduce the aldehyde. So you'd get the amine, and then you'd get an alcohol over here. And you could theoretically oxidize the alcohol to an aldehyde again, but to be honest, I'm not sure what oxidizing would do to the amine. I don't know if it would do any side reactions with it. If I was doing this on a test, I would probably avoid this route just because I'm not sure. And I'd rather be safe if I'm not sure. Because we can do something to kind of avoid that reaction affecting both of the groups. What can we do to the aldehyde to help stop it from getting reduced? It has been a while, but remember if we formed acetals, those were protecting groups. They would stop aldehydes and ketones from doing unwanted reactions like this one. So that's something we can do. The exact acetal we form doesn't really matter. I'm going to show it with this style, but you could also add 2 equivalents of whatever alcohol you want. And then the conditions just have to be catalytic anhydrous HCl. So it doesn't have to be this exact acetal, just any. Here. And it won't do anything to the amide. So we form this acetal, and now we can reduce the amide. Okay, so we reduce it to an amine, and at the same time, the H3O plus here is also going to return the acetal to an aldehyde. I should say reverse, not return. Because those are the conditions you need for that water and acid, which we have there. So now we have an aldehyde and an amine. Oops. we just have to make them react to form that final product. And we need specific conditions to do that. They won't just react with each other just by existing in the same molecule. So what conditions should we use to make them react? And this is another thing. It's been a while since you might have thought of it, so it's okay if you don't remember. Just make sure to review it for exams and for the final. For this reaction, it's pH 4.5. That's what you need to make aldehydes and ketones react with amines. And I'll just show like the nucleophilic attack. Like this is kind of in general. Like I'm not going to show the full mechanism. You could, and it might be good to practice, but this is kind of that nucleophilic attack, the amine attacking the carbonyl carbon. And then like if you number the atoms from the nucleophile to the electrophile like this, and then you number them in the product, you can see that like the methyl group was on atom 5 here, it's on atom 5 here, and it's a 7-member ring. So like we get the products we were trying to get. That's just good to make sure that that's what we got. So that's that. And there might be other ways to do this, but I think this is the most direct and straightforward way to do it. Okay, so any questions about anything here before I move on? Like I prefaced with, I don't think you'd have something like this on an exam. Like I honestly don't think you'll have an intramolecular reaction in a synthesis. You will definitely have intramolecular reactions in other contexts, but in synthesis, I think it's less likely because it's just kind of hard to think about a lot of the time. So if you were tripped up by this when you looked at it before coming here, that's okay. I think it's less likely to show up than other kinds of problems. Okay, last one. I'll try to get through this relatively quickly. Starting with an alcohol and an acid chloride. And we end with an amine where the alcohol was. So we converted the alcohol, or not an amine, we converted it to an amide. And then we converted the acid chloride to a, because that's where the acid chloride was at the beginning. And we added to ethyl. So all little notes to maybe make to yourself, either mentally or on a piece of paper. And another thing I think is a good idea is to consider, like, if you have alcohols, what kinds of alcohols are they? Like primary, secondary, or tertiary? It's like the one in the product is tertiary. And what's the one we start with?
Primary.
Yeah. And that's good because like primary alcohols might be oxidized differently from secondary, which would be oxidized differently from tertiary. And like a tertiary alcohol, like there are specific reactions that will specifically make a tertiary alcohol. So if you recognize that, that kind of helps you figure out how you're going to make that. So like just looking at the alcohol to start with, like an easy way to both add like ethyl groups, which we're doing, and make a tertiary alcohol would be a Grignard reaction. Because like if you do that with a carboxylic acid derivative, it will add carbons and make a tertiary alcohol. We have a carboxylic acid derivative here. We want to turn it into that, so this reaction makes sense. But before we can do that, we have an alcohol here. And remember, this will react with a Grignard in an acid-base reaction. So we have to do something to it before we can add the Grignard. It's going to be similar to the acetal formation we did in the last problem. So it's like another protecting group. And it's been even longer since we saw this, but does anybody remember what it is?
The OTOS one.
TMSCO.
It's pretty similar to OTOS, but, well, it sounds similar, but yeah, it's TMS chloride. So OTOS like is a better leaving group than an alcohol, but TMS is a protecting group. It'll stop it from reacting. So these are the conditions. It has TMSCl, and then you need some sort of base, usually triethylamine, so just free ethyl groups attached to a nitrogen. And that will make this. And now we can add a Grignard, and the alcohol is protected, so it won't do anything to mess with it. Specifically, we're adding an ethyl Grignard because we want to add those ethyl groups. Don't forget, you need ether for the first step and acid at the end. And just like the acetal gets deprotected when you add acid, the TMS group will get deprotected when you add acid. So we're going to get the alcohol that we started with again, just because we added alcohol, or we added acid in the second step there. So we have our alcohol here. Now we just have to convert the alcohol that we still have into an amide. And I'll just kind of go through it. I'm already low on time, over the time, but like you can't do this in one step, but what you can do is you can oxidize this because it's still a primary alcohol. You could oxidize it with any strong oxidizer. It doesn't matter which one you pick. I'm gonna put CrO3, but KMnO4 or NaCr3O7 would work too. Just any strong oxidizer works here. And this looks kind of like 7-numbered ring. This would convert that alcohol into a carboxylic acid. And we do have another alcohol, so you might worry that it will also oxidize that. But remember, this is tertiary, and you can't oxidize tertiary alcohols. So nothing's going to happen to that now. And then last, we just have to convert the carboxylic acid to an amide. So just add the nitrogen we want, and then we have DCC because we're using a carboxylic acid. And how you could do that. Okay. And like usual, there's probably other ways to do this, but this is the most straightforward way I could think of for this problem. But if you have something else, it might be correct too. Okay, so if there are any questions, feel free to ask. If not, I'll see you guys on Thursday and hope you have a good rest of your day.
Thank you, Nick. See you later.
See ya. Bye.